Hello everyone. So in the last class, we studied the CW operation of a CO2 laser, the pulsed operation of a CO2 laser, the pulsars that are involved in the single shot and repetitive operation of CO2 lasers. And then we turned our attention to the emission feature, spectral features in the emission of a CO2 laser. Before going on to the actual study of emission features, we started with the reason why the excited energy levels are not discrete energy levels, but there is certain broadening that is associated with them. There are several types of broadening, and we started with the first one, which is called lifetime broadening or spontaneous broadening, fluorescence broadening of the upper level, which arises because of the definite or the lifetime which is associated with an excited state. The excited state cannot, the molecule cannot remain in the excited state forever. It has to come down. So there is a definite lifetime which is associated with the excited level. And because of this delta T, there is a corresponding delta E because of the uncertainty principle, which says delta E delta T is greater than or equal to h by 2 pi. So for every delta T, there is an associated delta E, and therefore the excited energy level has a broadening in terms of energy as well. This broadening is a function, or it depends upon the properties of the excited level. And every excited level will have certain broadening. The next kind of broadening that we saw a little and we touched upon was homogeneous broadening, where we took an ensemble of identical molecules. For example, we have taken an ensemble of CO2 molecules at certain pressure, and we tried to pick each molecule, or this can be, as I said last time also, this species, it can be atom or molecule. So we pick one molecule and we try to see, we excite it, and when it gets de-excited, we want to see what is the emission of, what is the frequency of the photon that is emitted. So when we repeat this experiment n number of times for atom 1, we get this upper profile. This is the fluorescence profile. Now we go on to a second atom. Again, we do the same experiment. We excite it and try to see what is the frequency of the emitted photon. And if we repeat this n times, we get a second fluorescence profile which corresponds to the atom 2. And we see that it is just identical to what we saw for atom 1 or molecule 1, the species 1. So in this manner, we try to see for all atoms, all molecules in that ensemble, and we find that the fluorescence profile is the same for all of them, and this gives the combined fluorescence profile for the species, which is same as for each species. That means that upon excitation, any species will emit spontaneously at a given frequency, which could be nu0, nu1, nu2, nu3, within this fluorescence profile with equal probability. That means all species are identical. They are indistinguishable with regard to their emission feature. Conversely also, suppose you have species in the ground state, and if it is shown by photons, say of frequency nu1, then the probability that it will get excited is this, which is same for all species. So the probability that a photon of a particular frequency will interact with any of the atoms or molecules of this particular ensemble is identical. And therefore, such kind of broadening is called homogeneous broadening. The spectral profile of homogeneous broadening is given by Lorentzian line shape function. And one of the very common examples of homogeneous broadening is collision broadening. We have seen how collision actually affects in the lasing process of a CO2 laser. See, due to collision, the molecule which was in an excited state is forced to come down even before it's actually even before the time dictated by its lifetime. For example, we had seen that CO2, which is in 100, on colliding with CO2, the ground level, comes down to, gives rise to two molecules in 0, 1, 0. So the lifetime of this CO100, CO2100, which is decided by the spectral properties of that particular level, is curtailed because of collision with another molecule. So this collisions, if we take same species, for example, I am considering an ensemble of CO2 molecules, then the probability of collision is identical of one molecule with another and the second with the third, or one with nth molecule is same. And therefore, this collisional broadening is called homogeneous broadening. Similarly, thermal vibration induced broadening and natural broadening that we just studied before this, these are all homogeneous types of broadenings. Now, there is another kind of broadening, which is called inhomogeneous broadening. This broadening, as the name itself suggests, it is called inhomogeneous because the probability of emission of frequency can differ from one group of species to another group of species to another group of species. For example, let us now consider of such molecules, and then we do the same experiment as we had done before. We try to pick one molecule, excite it, and try to see its emission. We do it n number of times and we get something like this. Okay, we get a spectral profile which is like this. Now we take another molecule, again try to see the same thing. We may get a similar profile, somewhat like this here, identical profile. Again we take another molecule, try to see its profile, and then what we get is something like this, which is different from what we had seen for the previous molecule. Now, if we continue this for the entire ensemble, then what we see is that you can actually divide the species in your ensemble into several groups based on their fluorescence profiles. What you see is that there is a group which has identical emission profile, where the central frequency is mu0 and it dips on either sides. There is another group which emits at mu1 as the central frequency with the fluorescence profile dipping on either sides. Similarly, there is another group at mu2, there is at mu4, mu5. So this total broadening of this particular system is therefore the outer envelope, as we can see, of the combined fluorescence profiles of individual groups. So why do you have then these individual groups where you see that there are molecules which have similar identical fluorescence width? That is because, see, whenever you have an ensemble, there is natural broadening always. There is also some amount of collisional broadening depending on the pressure that you have taken. So they will always be associated with such kind of group of molecules, some homogeneous line width. So this is actually the homogeneous line width, which is decided by the natural broadening, by the collision, the pressure that is taken. And therefore, there is a group which has similar emission profile or fluorescence width. But altogether, when you see the entire ensemble, you see that there are different groups. And the total emission width of that ensemble is a resultant of a combination of all this, which is given by this outer profile. So here we can understand that the species in this particular ensemble are not identical with respect to their emissions. And therefore, this kind of broadening is called inhomogeneous broadening. Now, one very common example of this is Doppler broadening. I hope you know what is Doppler effect. We will just see very briefly what a Doppler effect is. You must have heard of it in sound, in the context of sound. That common example given to us is that when a train is approaching to us on a platform and whistles, then the frequency of the whistle appears shriller. That means the sound appears shriller, means the frequency appears to have increased. On the contrary, when the train is moving away from us and we are standing and the train whistles, then the frequency appears lower. Why does this happen? This is because of the Doppler effect, that when the train is approaching with a velocity v and also makes a whistle, then the sound waves are also approaching us, and in the distance that is between us and the train, they get compressed, and then the frequency appears to have enhanced. Same thing also happens in case of light. So what we have here, for example, you will see that this is a molecule which, when excited, goes to the upper state E2, and when it comes down, it emits a frequency. Central frequency is nu zero, which is E2 minus E1, that is the energy difference divided by H. Now, when this species or molecule is at rest, and it can emit in any direction, and the central frequency will remain same, nu zero here, nu zero here, or nu zero here, in whichever direction it emits. Because this is at rest, the observer, the other molecule or whoever sees it, it will be nu zero. On the other hand, suppose this molecule is now moving with a velocity v in the positive x direction, and it also emits a photon in the positive x direction. Then the frequency of the emitted photon as perceived by another molecule here will not be nu zero, but it will be shifted. And how it will be shifted? This nu one is equal to nu zero into 1 plus v by c, where v is the component of velocity in the direction it is moving. Similarly, if the molecule is moving in the positive v direction but emits in the negative direction, that is, if it is moving in the x direction with a velocity v but it emits in the negative x direction, then how will it be perceived by an observer here? Will it be nu zero, or will it be enhanced? Will it be blue shifted? No. Now it will be red shifted, and it will be given by nu2 is equal to nu zero into 1 minus v by c, where v is the velocity, which now is in the negative direction, right? So basically, there is either a red shift or a blue shift of the frequency of emission as perceived by the observer, depending on the relative motion of the emitter, at which here, in which case, is the molecule, and the observer, which will be another molecule which is there to absorb it, or to absorb it, right? So it basically depends on the relative motion, and therefore the molecule, although its central frequency of emission is nu zero, it can emit at various frequencies depending on the component of velocity it has in the direction of emission. Now, suppose I just ask you that this atom is moving in the bi-direction. Okay, so that means we have this molecule or atom which is moving in the positive y direction, and it emits a photon in this direction. Okay, so then what would be the change? Can you just think and tell what will be the nu that it will emit, and what is its relation with nu zero, which is the central frequency? Will it be red shifted? Will it be red shifted, or will it be blue shifted, or will it be at the same frequency? Just try to think. So now we have an ensemble of molecular species where we have at a particular temperature, and therefore all these molecules which constitute this particular ensemble, they have a velocity spread which satisfies the Maxwell velocity distribution. So you have molecules moving in all directions, and they follow this velocity distribution. Now, suppose we consider those molecules which have some component in the x direction, right? Which have some component in the x direction. And we try to see what would be the emitted frequency if the emission is also in the x direction. Suppose we are thinking that the molecules or atoms are moving in the x direction and the emission is also in the x direction. So how will the emission of this entire ensemble look like? Now we are saying which has a component in the x direction. Suppose I say that there is no component of velocity in the x direction. Then which are these molecules? These are the molecules which are moving in y or z directions, which have components of velocity in y and z directions, but no component of velocity in the x direction. Such number of molecules will be the maximum, and therefore what will be their emission frequency? Because they have no component, the x direction component x vx is 0. Therefore if they emit in the x direction, then the frequency nu should be equal to nu 0 into 1 minus v by c. V is 0, so this will not be there, so that will be equal to nu 0. So we will have the maximum number of molecules which do not have any component in the xy direction. That number will be maximum, and they will emit at the central frequency, which is mu 0, and the spread that will be there based on the pressure as well as based on the natural line broadening. So we will have highest point, which is by the molecules which are moving in all other directions but have no component in the x direction. Now you consider another group of molecules which have, suppose, velocity v1, okay, v1 in the x direction. Now when it emits also in the x direction, so what will happen? The nu that will be emitted is nu 0 into 1. It is also emitting in the x direction, and your observer is here, so it is also moving in the x direction, so it will be 1 plus v by c. So the frequency will be blue shifted, and therefore the new frequency that will be perceived as emitted by these species will be nu 1, which is blue shifted. And once again, all these molecules which are having a velocity v1 will have their own natural spread, and therefore this is the curve that we see, which is emitted by those group of molecules which have a velocity v1 in the x direction. Now if you have another group of molecules with higher velocity v2 also in the x direction, then their emission in the x direction will be further blue shifted. So this is what you see, it is further blue shifted, and now as the velocity component increases and increases, the number also comes down as per that distribution curve. So the number comes down, so this probability of emission also comes down, and you have the natural broadening associated with that group. So it continues like that. Now for every group of molecules with a velocity v1 in the x direction, you also have an equal number of molecules moving in the minus x direction. That is, they are minus v. That is, they are not moving in positive x direction, but they are going in the reverse direction. They are going in the reverse direction. So the velocity molecule is moving like this, but suppose it is emitting in this direction. We are considering just the positive one direction emission. So if it is emitting in this direction, so then what would happen? Then it will be, the frequency will be red shifted. The nu will be nu naught into 1 minus v by c. So it will be red shifted, and you will have a frequency which is less than nu 0. And once again, the amplitude of the probability of emission, or the number of photons that you will get here, will be proportional to the number of molecules which are having that kind of velocity. As you go further, now for every velocity component, every velocity value here, you have a corresponding one in the negative x direction, and therefore this will be a kind of symmetric curve, and the total broadening. Therefore, when you have this kind of an ensemble, when you will try to collect all the the photons that are emitted through fluorescence, you will see that the frequency is not just nu 0, but it extends on plus on the higher frequency side, which is blue shifting, and also on the lower frequency side, which is red shifting, and the total fluorescence width will be will be an envelope which covers all of them, all the individual probabilities. And this is, as we have shown here, all groups together will have this kind of a fluorescence width. Okay, so now you have understood that when you have a group, an ensemble of molecules at a particular temperature, because they have their own they have their own velocity spectrum. Each group has its own velocity spectrum, so they are not identical, and therefore the emission that they have, the fluorescence profile that they exhibit, is also not similar to each other. And therefore, when you have a system which is predominantly inhomogeneously broadened, you will have this kind of a spectrum, and all species in it are not identical. They have their own they have their own fluorescence spectrum, and the overall effect of that ensemble is to have a total width. Now, while this would be the homogeneous width, the total width now is somewhat like this. If you think of full width at half maximum, you know what is full width at half maximum, no? So if this is the peak, then what is the spread at half of that? Okay, so this will be the total spread, then frequency spread of this particular ensemble. So this is called inhomogeneous broadening, and Doppler broadening is one very common source or common reason for inhomogeneous broadening. So now we know what are the various types of broadenings. We have seen homogeneous and inhomogeneous. In case of homogeneous, we know that this line broadening is there, the collision broadening is there. Then we have inhomogeneous broadening, which is velocity broadening. And when we consider gaseous laser, like a CO2 laser, all three will always be present, because line the very first broadening, that is that which is associated with lifetime broadening, is always there, which is an individual property of these particular levels which are participating in lasing. So that anyway is there. Because we are taking molecules at a particular pressure, so you will have collision broadening, and they are also at a particular temperature, and at that particular temperature they have a certain Maxwell-Boltzmann distribution, and therefore there will also be some Doppler broadening. Important that we have to consider is which broadening dominates when. So now let us first consider the what we expect when we have a CW CO2 laser which operates at low pressure, say for example at 10 torr. So at that typical gas pressure, like we say 1:1:4 or 1:1:5, where 1 and 5 are CO2, nitrogen and helium respectively. At that kind of typical pressure, the broadening, collision broadening, is given as about 5 megahertz per torr. Why we are saying for that particular gas mixture? Well, because it is not a single gas ensemble that we are considering. We are considering a gas mixture, and depending on the sizes of the molecules or atoms that constitute this particular mixture, the collision rates of all these are going to be different. But as a whole, this is an average broadening that one expects, which is 5 megahertz per torr. And therefore, so if we have about 10 torr pressure, then we say that the total broadening associated with collision is about 50 megahertz. And the Doppler broadening at that particular temperature we consider about 400 degrees is the Celsius, is the 400 degree Kelvin is the discharge temperature. So you know that Doppler broadening will be proportional to under root T by N. Right? T is the temperature. As we increase the temperature, the Doppler broadening will increase. Similarly, as we increase the pressure, the collisional broadening will increase. So the Doppler broadening can be calculated to be about 50 to 60 megahertz at the operating conditions, and therefore we can say that this collisional broadening as well as Doppler broadening are nearly similar, and the total broadening will be a convolution of the two. Doppler broadening, I said that a line shape function for collisional broadening is Lorentzian. For Doppler broadening, it is understandably Gaussian. And the total broadening is a convolution of the two kinds of broadenings. So we already had seen that when we create inversion CO2 laser, whether it is CW or pulsed, so various rotational levels get populated in the lower as well as upper level. We assume that in the lower level, that is 100, for example, here, the population is very small. Maybe you should not even consider this much. It is much less. The population is much less because we have selective excitation into 001 with the presence of nitrogen also. So the population inversion is large, and depending on the temperature, you have some rotational levels which have higher population as compared to the other, and we know that this is the way in which the rotational population is distributed among various rotational levels. So initially, as pumping begins, the line with the highest gain. So we have normally, it could be, in case of low pressure, it could be 10p 20 or 10p 18, which under those conditions generally has the highest gain. So this gain, the gain on every transition rises, and the one which reaches the loss line first, if the stimulated emission sets in on that particular transition, and lasing gets initiated. When lasing gets initiated, the population in that particular level starts reducing. Right? The population starts reducing, and when the population starts reducing, the gain also then it reduces. Then the stimulated emission rate also reduces. Right? Now, when the population reduces, then there is a rotational thermalization. What is rotational thermalization? The molecules which are present in various rotational levels, because the separation between these energies is very small, we say it is less than 2 centimeter inverse or so. So it is much less than the KT, and therefore there is a rotational thermalization. That means ensemble, the molecule, again tries to get back this particular shape. Although it is falling like this, there is a burning of the population. It tries to maintain and get back this particular shape, and this lasing tries to continue. However, if our pumping rate is a little fast, then it is possible that initially 2 or 3, like these two levels, may reach the loss line nearly at the same time, and before this rotational thermalization takes place, some lasing may set in on this also. Eventually, there will be a tussle or a competition between the two, and generally it is seen that one of them continues to lase, and you get lasing on either 10p20 or 10p18. Sometimes there is a jump from one to another, and that can be attributed to some variations in the cavity length, etc., because of which the gain on one increases than the other. So today we have studied about the various kinds of broadenings that are associated, that we get to see very commonly in case of gas lasers or even other lasers. In case of gas lasers, all three, this natural broadening, collisional broadening, Doppler broadening, all these are present. But then depending on the kind of operating conditions, either one of them will be predominant, or they may be, as we have seen in this CW condition, the Doppler as well as pressure broadening are nearly same.